Okay, with unit 3.7, we're going to shift gears a little bit. We've been talking about mostly gases, and earlier in the unit we talked about solids, but we haven't really talked about liquids, and actually in terms of liquids we're going to talk about solutions. So if you take a solid, or I guess you could take a gas and dissolve it in water maybe, you'd get a solution. So in terms of solutions, there is a solute. That's typically maybe a dry material, maybe like NaCl, and you dump it in water, and water would be the solvent. And depending on how much salt you dissolve in the water, you would have a different concentration. And those concentrations can be measured in described in a lot of different ways. We'll typically use molarity to describe the concentration of a solution, and that is moles of solute divided by liters of solution. And we're typically going to use a factor label method to be able to solve for whatever questions deal with that. So these would be probably more multiple choice questions when we would get to a test, but we'll work this out in a free response kind of mode here. So to do a question like this, what's the molarities of sodium and phosphate ions in a sodium phosphate solution? You have to know what sodium phosphate is. So you really have to be good with your polyatomic ions and regular ions for that matter. So sodium phosphate would maybe appear to be that, but you have to be aware of what charges these things have, and a plus for sodium and a -3 for phosphate. So that would mean that you would have, let me erase this, you would have 3 sodiums for every 1 phosphate. Now when you dump that in water, you're going to get 3 sodium ions, and you're going to get 1 phosphate ion. So if you had 0.25 molar sodium phosphate, you have 3 times that. That would be 0.75 molar Na plus ions. And then you would have, it's a 1-to-1, so you'd also have 0.25 molar of the phosphate. And that's how you would do questions like that. So you have to be aware of the charges and how to build the molecule up, the compound up, and then go from there. So you always need these coefficients here to be able to solve a question like that. Another typical question. So this would more likely than not be maybe a laboratory kind of question where you had to do something else and with a 2 molar solution. Well, how are you going to make a 2 molar solution? So to make a 2 molar solution, we'd have to figure out how many grams to dissolve in the water there. So I go on the periodic table and find sodium chloride, and it's about 58.5 grams of sodium chloride, in 1 mole of sodium chloride. Then that gives us the grams that we would love in our answer, but we got to get rid of the moles on the bottom of this fraction here. So what else do we have? We have 2 moles of NaCl dissolved in 1 liter, and I'm going to write 1,000 milliliters instead. Why? Because 1,000 milliliters is 1 liter. So that was this. So this big M is moles of solid divided by liters of solution. And then we were told that we're going to make 250 milliliters of it. So I think all of our units will cancel, except for the units we want in our answer. And yes, we will be left with grams. So when you multiply and divide everything out there, we're going to get 29.3 grams of NaCl would be required. Okay. Similar question, but now we are given the grams, and we're given that we are making a 2 molar solution, but this time we want to figure out the milliliters of that. So many of these questions are all kind of the same. You just have to decide where you want to start with your factor label. Where I like to always start, it doesn't mean that that's where you have to start. I like units that I'm going to have in my answer. So my answer's got to have milliliters. So I'm going to have a unit that starts off with milliliters. So I have provided for me the molarity of the glucose. Okay, so that 2.00 big M is moles per liter. You could put the moles up top if you'd prefer. You can put the milliliters up top if you prefer. I prefer the milliliters because that's going to get me my unit that I want in the right location. So it's like saying 12 eggs equals a dozen, but also a dozen equals 12 eggs. So it's dependent on what are you trying to solve for. You're trying to solve for how many dozens, or are you trying to solve for how many eggs? In this case, we're doing milliliters, so I have the milliliters part up top. So I'm going to have to get rid of the moles. The molar mass is provided for me. Sometimes that'll be done for you. So if the molar mass is given to you as 180, you're going to use 180. Don't go on your periodic table and try to do your own molar mass if it's already provided for you. So I'm going to put the moles up top and then the 180 grams on the bottom. Why? So my units cancel. My moles and moles cancel. And then I was provided with 9 grams of glucose. And I think all my units will cancel at this point. Let's double check. Moles and moles, grams and grams. So we will be left with just milliliters. And when you multiply all that together, I think that's going to come out to be 25.0 milliliters. So if you're trying to make a solution, you have a couple different options depending on what the materials are. So lots of times you're going to use grams because you're going to have a dry solid, and you're going to have to dump that in water. So that would be this technique number 1. And to know the specific volume of water that you're using, solution that you're making, I should say, we have to use a piece of equipment called a volumetric flask. So if I ever ask, or if the AP test question asks about making a solution, you're always needing to use a volumetric flask. And a volumetric flask looks a little like they have different shapes at the bottom here, but it's wide at the bottom and a very, very thin, long neck close to the top. And then it's always labeled with an amount. I think our last question was 250 milliliters. So this volumetric flask is only good for measuring 250 milliliters of liquid. And it'll have an etched line somewhere on the neck. You want to put some water. How much water? Just put some. It doesn't necessarily mean, it's not really defined. But the reason why you're going to put a little bit of water in there first is because if you add your solid material to the bottom of this flask and then add water to it, the solid kind of cakes up, sometimes sticks to the glass, and it'll make it troublesome to get that to dissolve. It'll just take a lot longer. So a lot of people will add a little bit of water first and then add the dry chemical and then volume up. So that's an important word. How about if I do my V's better? volume up to the etched line. And where exactly do you want to go? Well, the water is attracted to the glass, and it's going to create a meniscus. And you want the bottom of the meniscus to be right up on that line. So that is where we want to go with the voluming up, okay? Sometimes you might have a solution already and you have to make a dilution of that solution, just meaning that you're making it less concentrated. So in that case, we can use, you can do factor label and that would work perfectly, but you can also use an M1, that's a molarity, a V1, that's a volume, equals a new molarity and a new volume. To measure liquids, you're going to have to use a volumetric pipette. Some people will use a graduated cylinder, but a volumetric pipette is thinner with more increments, so it's going to be more precise. Above, with the dry solution, the dry material, technique 1, you'd have to use a balance. And you'd use the best balance you have available to you, meaning the most decimal places. So you'd measure out your amount of liquid, and you dump it into the volumetric flask again, and then volume up to the etched line, just like we did in technique number 1. For safety reasons, if you have a situation, which I don't think is going to arise in class, but if you had to mix acids and water, meaning concentrated acid with water, water has the ability to dissipate heat. Well, it absorbs a lot of energy before the temperatures rise to a dangerous level and boiling would occur. Most other substances, that doesn't happen. So when you add concentrated acid and water together, a lot of heat is generated. So we can do it safer if we add the concentrated acid to the water as opposed to the other way around. Okay, so we have a hydrochloric acid solution. How do I know it's a solution? 12.0 big M, that's molarity. And we're trying to make a new molarity. So that's a dilution. So we can use that M1V1 equals M2V2. So it doesn't really matter which ones are 1s and 2s. We have 12 molar. We don't know how much of that we want to use, but we want to make 100 milliliters in a volumetric flask. It's always going to be a volumetric flask. And we have a 0.5, we want to make a 0.5 molar solution. Okay, so I think it might be obvious, but the answer better be less than 100. You can't physically be able to put more liquid than what the container can hold. So when you do that math, you're going to get 4.17 milliliters. So it'd be 100 times 0.5 divided by 12. Now, to make that happen, I don't think you'd be able to use a graduated cylinder because you wouldn't be able to get precisely 4.17 milliliters. But with a volumetric pipette, that might be possible. How many grams are required? Okay, so go on the periodic table, find the molar mass. We had already done that with a previous question for sodium chloride. We were given a 0.1 molar solution, which means 0.1 moles of NaCl in 1 liter or 1,000 milliliters. And then we were told we're supposed to make it in a 500 milliliter volumetric flask. It's never going to mention that, or rarely it's going to mention that, but we're always going to use a volumetric flask. So 58.5 times 0.1 divided by 1,000 times 500, and that would require us to use 2.9 grams of NaCl. Okay, so kind of piggybacking the items about solutions is a type of laboratory technique called gravimetric analysis. Basically, it's filtering. And you guys may have done some filtering last year, or at least talked about filtering last year. And so you could have a chemical reaction. Let's make a chemical reaction here. We have, like, I don't know, A plus B making C plus D. These are just all generics. And maybe one of these chemicals is an S, a solid. It's a precipitate. So if we know how much of this we made, we can figure something out about one of the reactants. Why? Because the reactants and the products all have coefficients. In this case, I just made them ones, but they might be twos, it might be threes, whatever. And that those coefficient ratios are mole ratios. So we can know if we had this many moles of this, how many moles of that we had. If you don't filter correctly, so you're gonna make a dry, well, eventually dry, but when you're adding a solution of A and a solution of B together and making this precipitate, it's going to be along with a bunch of rest of more solution. The solution that you're making, the C, but also one of these is probably going to be excess. There's going to be some left over. So you have to wash your precipitate. That means get rid of all the other chemicals that might be attached to it. You have to completely dry it. And why would you have to dry it? Because if you don't, water will be attached to that chemical and it'll have an incorrect mass. It'll weigh too much. And then, and only then, will you be able to walk backwards to figure something out. So let's try to do one of those questions. So this would be a typical kind of question. So an ionic compound contains chloride and something else. Dissolve it in water, and then someone precipitates using AgNO3. Silver ions precipitate with almost everything. So they certainly will precipitate with the chloride ions. So someone then dries, washes the precipitate, well, filters, dries, washes and dries the precipitate, and this is how much they get. So now we can walk backwards. So many of these questions are factor label, and if you know where to start, and the reason I'm starting here is because that's my precipitate, and that's always a good place to start. Well, it has grams. Is there anything I know that I can get rid of grams? Yep. I could go on the periodic table and find out how much 1 mole of AgCl weighs. And I think it's in the 143.32 range if I look up an Ag and a Cl. Okay, so now my AgCl grams cancel. But I'm not interested in AgCl. I'm interested in chlorine. So this might look like you don't need to do this, but I think this would get us where we want to go. In 1 mole of AgCl, there is 1 mole of Cl, or Cl minus. It doesn't really matter. They're going to have the same masses. Okay, so moles of Cl, but we want to do mass percent. So that means we need masses. Well, let's go back on the periodic table and find out how much a mole of chlorine weighs. Okay, so we'll do that, multiply, divide, and I get 0.269 grams of chlorine. So whenever we're doing percents, it's always parts divided by total times 100. Well, now we have our part, 0.269 grams of Cl. We have our total. That was given to us in the question. And then to get it in percentile, we just have to do times 100. And that's going to be 47.54% chlorine by mass. There we go. So factor label is definitely going to be one of your go-to problem-solving techniques. And you just have to make sure you write your units down and you get them to cancel. Okay, so another filtering question, or we can call it a gravimetric analysis question. But this time, we're given a little more information. A reactant and a reactant. So let's go through and try to figure out what this chemical reaction is. FeNO3 plus Na2. So iron nitrate plus nitrate plus sodium carbonate. It's a double replacement, so the Fe's and the Na's are going to switch spots. And every time you make one of these molecules or make one of these compounds, you have to be able to balance those charges so it works. So it's a neutral compound. So Na plus and NO3 minus, you need one of each of those. And then the other compound, Fe with carbonate. Carbonate has a -2 charge. And Fe, because it was in this compound here, had a +3 charge. Okay, so now we're going to have to balance this. We'll put a 3 there, we'll put a 6 there, and we'll put a 2 there. So now it's a 2 to 3 to 6 to 1. I wouldn't normally put a 1 there, but we'll put a 1 there. It doesn't tell you what the precipitate is. So now you have to know your solubility rules. NAs with NO3s, no matter what Na plus is with, no matter what NO3 minus is with, it's always soluble. So that would mean that this must be our precipitate. And you don't have to put that little S there. I'm just doing it so we know which one's which. So it gives us the precipitate. So we're just going to have to walk backwards, that's all. So we have 2 grams of the precipitate. That's the iron carbonate. And to get rid of the grams of iron carbonate, I went on the periodic table and I found out that iron carbonate weighs 291.7 grams. Okay, so now I have moles of iron carbonate and I want to get to iron nitrate. The ratio between those two is a 2 to 1. And then it says how many grams, so we have to go and use our periodic table again. And 1 mole of iron nitrate, there are 241.85 grams of iron nitrate. Okay, and multiply everything on top, divide everything on the bottom. You get 3.316 grams of iron nitrate. Factor label again. But if you didn't have a balanced chemical equation, you'd never be able to do that question. Okay, so definitely we'll pluck some multiple choice questions out from previous AP tests. So what do we got here for our first one? Equal volumes of solutions in two different vessels. If the solution represented in vessel 1 is KCl. So KCl is 1 potassium and 1 chlorine. So it looks like we have 4 and 4. 1, 2, 3, 4. 1, 2, 3, 4. Okay. What does vessel 2 have? Well, can it have KCl? Well, if I look at those, I'm not going to count those with my pen, but I think you can see that there's not the same amount of the black and white circles. And for KCl, it would have to be the same, 1 and 1. So that means it cannot be those two answers. So how could it be calcium chloride? So calcium chloride, if you dump that in water, you would get calcium ions and 2 chloride ions. So maybe we will count these up now. 1, 2, 3, 4, 5, 6, 7, 8. So if we have 8 calciums, we must have had 8 calcium chlorides, because it's just like that one was a 1 to 1 to 1 or a 4 to 4 to 4. If we have 8 of the calciums, we have 8 of the calcium chlorides. How many of these? We better have 16 here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And why do I know it's going to have to be 16? Because it has to be a 1 to 2 ratio. So does it have the same molarity? Well, it looks like it has double this. The vessel 2 has double the amount, so it can't have the same molarity. But does 4 to 8, does that double it? It does, so twice. So our answer is going to be D. I'm going to have to make that a little bit smaller so we can get that all in here. Okay, which of the following diagrams best represents silver nitrate solution? So let's look at water. So here's this is a little diagram of water. I kind of represented it as they're showing it. And hydrogen, you have to know that it has a partial positive, and oxygen has a partial negative. Why? Because electronegativity values, and oxygen attracts electrons more than hydrogen does. So to kind of keep that idea, you would have to have that. So coulombic attraction for oxygen in water would be the cations, like that right there. Not like that. The pluses of water and the plus of Ag plus, that's not going to attract. We like that for C. Are we also going to like that for NO3s? We'll visit that in a second. And this one, Ag plus and NO3 minus are together. That would mean that it's a precipitate, and that's not going to be the case. So right now we like A and C, but why do we like A better than C? Well, nitrate is a minus. It says it's a minus right there. So it's going to have to attract the hydrogen part of water, and that doesn't happen down there, but it does happen here. And our last question Question gives us what water might look like, and it gives us what the LIs and the CLs look like. By the way, the Li plus is going to be the smaller of the two circles, because ionic radii is in play here. Chloride is going to be the bigger one. Okay, I don't know if we need that or not. So it tells us up here in this this series of sentences what's going on. And then it says that we want to make a drawing that represents the different particles present in the solution. Based on the particles in your drawing, include only one formula unit. That means we need one Li plus and one Cl minus. Basically, we're going to try to do that. I'm not going to bother drawing all those waters. I'll probably just do one. So we have Li plus. It better be attracted to the auction part. And I guess if we want to keep this straight with what was given to us, let's go do that. And I'll put a little dotted line there. That dotted line means that that's not a covalent bond. It's just an intermolecular force. It is pretty strong, coulombic attraction there. So I could draw some more waters if I wanted to, but to save a little bit of time for this explanation, I don't think I need to do that. And there's the chloride, and it's going to be attracted to the other part of water, the hydrogen side of water, like that. And so I didn't give myself a lot of room for dotted lines there, but there's some dotted lines. And nowhere in this question does it actually mention that you need these dotted lines. So did we identify the ions, symbol and charge? I think we did that. Did we arrange them with proper orientation? I think we also did that. This question says you need one formula unit, so we did that, and no more than 10 molecules of water. I included one, and I think I properly oriented them, so I think I would get full credit there. And I think that might be it for today.